And let's start now with the first speech. Bigamel is honored to have here today and present Professor Thomas Dietterich, who comes from Oregon, US. Professor Dietterich, one of the founders of the field of machine learning, is here to talk about artificial intelligence progress, real-world stories, and long-term risks and the opportunities, as his presentation says. With a Ph.D. at Stanford University, he's distinguished professor of computer science at Oregon State University. He served as well as executive director of machine learning, helped co-found the Journal of Machine Learning Research, and was the founding president of the International Machine Learning Society. Professor Dietterich is currently the president of the Association for the Advancement of Artificial Intelligence. Please give him a warm welcome.
Okay. Well, it's a great honor and privilege to be here, and I'm going to begin by talking about artificial intelligence. And the organization of my presentation begins by talking a bit about the history in the last 10 years of the progress in artificial intelligence. And then I'm going to talk about three topics. The first topic will be about what I call tool AI, so AI como herramienta, and where the artificial intelligence, as with Google or Siri in the telephone, answers questions, performs tasks for us. The second topic I'll talk about then is what we call high-stakes autonomy, when artificial intelligence is put into a task or a position where it is making decisions that have high-risk consequences, maybe human life or large amounts of money. And then and I think there are many risks that we need to consider, that there are dangers in putting AI systems in control of these kinds of applications, and I'll talk a bit about those risks. The third thing I'm going to talk a bit about is technological unemployment. So to what extent is artificial intelligence going to be contributing to unemployment increases, and maybe what will be the jobs of the future? What might those look like? And then I will conclude the talk by thinking about the next 50 years or 100 years of AI as the technology continues to progress. Where is this taking us in the long run? So what is artificial intelligence? Well, we think about it as smart software. So it includes many components. One of them would be perception. So vision and speech, touch, perhaps. Even there are people working on artificial nose or artificial tongue for taste, chemical analysis. So these kinds of perceptual capabilities. And so this is an image here, a photograph from some research at Stanford University by Fei Li and her students on trying to teach a computer to describe the contents of a photograph. And of course, in machine learning, the standard way that we do machine learning is to provide what we call the training example. So in this case, the training example is an example, let's see if this works. Yes, where we provide the image and then a description of the image. So in this case, someone wrote the sentence, "This image has a woman in white, in a white dress, standing with tennis racket, two people in green behind her." And then we call it annotating or labeling the image to put rectangles around the relevant parts. So here's the dress, here's the woman, the tennis racket, and so on. And the job of the machine learning algorithm is to learn, given just the photograph, to produce the language that describes it. So that's the perception part of artificial intelligence. The second aspect of artificial intelligence is reasoning. And one way to think about that is choosing a sequence of actions in order to achieve some goal. So planning a sequence of actions, logistics, scheduling, things like this. The third component of intelligence is learning, and of course machine learning is now the most dominant way by which we create artificial intelligence systems. And finally, an important aspect of artificial intelligence is being able to understand and predict what's happening in the context around the system. It's not enough for the system itself to make good decisions. It needs to understand what the people and businesses and the natural environment, how are all of these things behaving. So there's been a very large amount of progress in the last 10 years, although it really reflects steady progress in the 60 years since the field of artificial intelligence really began. One example of that progress is in speech recognition. So many of you have probably used the Google speech search, where instead of typing your query, you just speak to your phone and then it answers. And they measure the accuracy of the speech recognition in the percentage of words that are incorrectly understood by the system. And in 2013, the word error rate was 23%, and only 2 years later, it's now down to 8%. And this mostly reflects advances in machine learning, particularly a technique called deep neural networks that has made this possible. Another example is also from Google, is the Google Image Translate, where you can hold your telephone up and look at a sign, and it will translate that sign into, in this case, from Spanish into English, and then render in the same fonts on top of the image. So this really combines two main capabilities. One is to actually find the text in the image and realize that some of the text is in a white letters on a red background, some of it is in black, and so on. And then the second part is the translation part. And if you read this, okay, the translation is not perfect, but it's certainly usable. And then, as I mentioned, there has been a lot of work just in the last year on having a computer program that can look at a photograph and describe what's happening. Of course, on the internet, it's a good guess that there's a cat in the image, so maybe it shouldn't get any credit for that. But it does correctly say this is a black and white cat sitting on a chair. And that's work from Berkeley, Trevor Darrell's group. And I could talk about many other advances in perception and computer vision. I'll just point out one more here. This is, as a function of time, the task here is to detect the presence of an object in an image. Does this image contain a car, a person, a cat, and so on? And if so, where? Located in the image. And starting in 2005, early systems were only getting 10 to 20% correct, and now we're up to about 60% correct. This is measured on a European-wide data set that was produced by the Pascal project. Leaving perception behind, let's think about reasoning. So one of the classic problems in reasoning is sort of the logic puzzle. We call it the satisfiability problem. So given a set of constraints, the question is there a solution to that set of constraints or not? And if there is a solution, what is it? So back in 1998, we could only handle problems that had 1,000 constraints in them, whereas today, more than 1 million constraint problems can be solved. And this has reflected many, many algorithmic improvements that are listed here. So it's not just that Moore's law is speeding things up, but more that we have improvements in the technology. Another kind of reasoning problem is reasoning under uncertainty. And a good example of that is the game of chess. And here the game of poker. So in poker, you don't know what cards your opponent has in their hand. All you see is the cards that are out on the table. And each unique collection of cards that is on the table we refer to as an information set. And in 2003, we could only handle information sets with roughly 10,000 configurations in them, whereas now, and this is a group from Michael Bowling at the University of Alberta in Canada, they were able to solve the game of heads-up limit Texas Hold'em, which has 10 to the power 13 information sets. Now here, it is true that 3 of those orders of magnitude are from Moore's law, and so the remaining 5 factors of 10 are due to algorithmic improvements. And of course, a classic challenge for artificial intelligence has been the game of chess. And computers defeated the best human player back in the last century, the last millennium. Now they are much better than the top human player. The game of Go from Japan has been much more difficult for computers, but there was an important advance right at this point that is known as Monte Carlo tree search that is now helping us improve. We're no longer playing at the average club level, but we're still very far away from the top level of human performance. So I want to mention another aspect of artificial intelligence, which is that often we find naturally the field works on trying to make the computer as smart as possible. But there's a change in direction to thinking about the combinations of people and computers working together. And these are sometimes called collaborative systems or sometimes called the centaur system because it's half man, half computer. And we often find that the combination of a person and a computer working together can be more effective than either one alone. And so one example of that is the problem of protein folding. So, the problem of protein folding is that you can be given the sequence of amino acids that makes up a protein, and then that protein somehow folds up to form a shape that gives it its biochemical activity. And there are the way they describe these proteins is they draw them as these things called ribbon diagrams. The blue ribbons here are the correct answer, the true answer, which was found by X-ray crystallography, which is a slow and very expensive process. The red was the best guess of the computer working alone, and the yellow on here is the work of a team of players playing a game called Fold It, which was developed at the University of Washington, in which the computer is trying to find the shape of the molecule, but the humans can go in and interact with that and make more strategic moves that the computer cannot see. So the way it works really is that the people are able to provide the kind of strategic decision making, and then the computer works out all the details and consequences of those. And this team, working in only 3 weeks, was able to develop the correct structure of this HIV enzyme. So this is really a very exciting achievement and was published in leading journals. So what is next now as we finish this review of the current state of things? Where are we headed? Well, as I said, I think there are two directions we can think about here. One is tool AI, so where AI is a tool for where the human is always in control. And this certainly includes the search engines, IBM's Watson, the personal assistants like Siri and Cortana and Google Now, and things like Google Translate and another very nice tool that's just coming out, the Skype real-time translation is now available between Spanish and English. So maybe we should be using it here. I don't know. The other direction, though, is autonomous artificial intelligence, where we are building an autonomous system, and part of its capability is due to artificial intelligence. So there are already a few hedge funds in Wall Street that are trading using AI algorithms. Of course, there are the high-speed trading systems that use typically fairly simple algorithms because they only have a few nanoseconds to compute. But people are thinking about self-driving cars, about automated surgical assistants, putting computers in charge of the electrical power grid, and of course, autonomous or semi-autonomous weapon systems in the military. Well, so I will talk first about tool AI and what I see as new directions there. So one thing is going beyond just saying if we present a computer a picture here, a caption might be several people playing American football. But what we'd like the computer to be able to do is have a much deeper understanding of this video and say, what type of play was this, right? We have the passing plays and the running plays in American football. Who was the person carrying the ball? If there was a pass, was it complete or incomplete? Which of the players made mistakes? Which of the players succeeded in achieving their objectives? So I think we will see this kind of thing in the next, say, 5 or 10 years. Similarly, if we think about natural language processing, this is, of course, a very long-standing challenge in artificial intelligence, is could we have computers that could understand documents, books, and so on. And this is still a very big challenge. What we would like to see, and I think we'll see soon, is computers that can understand this kind of text. So here's an excerpt from a news article that said, Pascal Yoadimnaji has been evacuated to France on Wednesday after falling ill and slipping into a coma in Chad. His wife, who accompanied him to Paris, will repatriate his body to Chad. And what we would like the computer to be able to do is answer questions such as, is Yoadimnaji dead? The story doesn't really say that, except that we know that it's talking about his body, so we can infer, yes. Is he in Paris? Yes. Is he married? Yes. Where is his wife? Well, she's in Paris. Where will she be in the future? She'll be in Chad. So those kind of inferences, right now, this is really beyond the capabilities of computers to understand. But I think, again, in the next 5 to 10 years, we should have this deeper level of understanding. Another opportunity I think that's happening, that's already been demonstrated a bit, is linking up big data to areas such as medicine or also maybe criminal policing and so on. So in this case, this was a study from Microsoft Research in which they looked at people's web queries, asking questions to Bing and Google and so on. And they were interested in trying to detect interactions between drugs. When a person was taking multiple drugs and had some bad combination of drugs, this is a very large space of possible combinations, and they cannot test them all in advance. So in the United States, there's something called the FDA Adverse Drug Interaction Reporting Service. And these are curves that compare how well the Microsoft Research System did to the US to the FDA. And when the green curve is above the red, that's where the web queries were actually more effective than the doctors. So this is one example of many possibilities in medicine. And finally, there is a new company called Viv that is a startup by many of the same people that built Siri. And they have this example as part of their company pitch. So suppose you want to be able to pick up your phone and say, on the way to my brother's house, I need to pick up some cheap wine that goes well with lasagna. And what we would like to do is have this improved personal assistant. Okay, maybe it doesn't really know what lasagna is, but it can go on the web and find out what are the ingredients for lasagna. And it will discover, oh, there's tomato sauce, maybe there's meat. And then it can go to a web, to a wine recommending site and find out, well, what kind of wine goes well with that? And maybe say, oh, Cabernet, maybe Rioja, I don't know. And then, of course, my brother's house needs to be able to look up the home address from the contacts on the phone. Identify possible routes to arriving at the brother's house. Identify the stores, the shops along that route that might have that wine for sale, and what prices they're offering, and then say, well, you should drive down this place and buy it at this store on your way to your brother's house. So this could all be possible if those various information sources could all be integrated, and that's their big challenge. Okay, so that's the future of tool AI, at least some guesses about it in the near future. Well, now let's think about autonomous systems and what the risks might be there. So, as I mentioned, there are many autonomous systems being considered, and partly they're being considered precisely because we've had these advances in artificial intelligence that say, whoa, now it might be possible to build a self-driving car or a surgical assistant that could do certain routine parts of surgery. So the motivations for such things are clear. We have these advances in AI. There's a tremendous potential to save lives or save money. And there's a need to act often at very high speed, which is something that people can't do, say in the high-speed trading cases. But I think there are many risks or dangers with this as well, and they really require additional research and development to address. And so I'm going to talk about 4 risks here. The first one is bugs. So we all know that software is often contains errors in it, programming errors, and this is true for AI-based software as well. In fact, it's maybe more true because machine learning algorithms only give a probabilistic guarantee of correctness. They're not correct all the time. And so here's an example in the image captioning case where the Stanford image captioning case said this is a young boy holding a baseball bat. Now, if we had a robot policeman responding to this, something very bad might happen, in the U.S. anyway. So the question is, how can we ensure the safe performance of AI systems when they're put into an autonomous system? We need some way that we can detect when the computer's making a mistake and either eliminate that in advance or involve the human in making the decision. A similar problem, of course, is cyber attacks. And there's been a lot of information in the news lately about cyber attacks against automobile computing systems and also against a sniper rifle. There was an example recently where people were able to break into a USB-enabled, Wi-Fi-enabled gun. Who knew such things existed? But I think AI systems also offer additional ways that they can be attacked. And one of the examples is known as training set poisoning. And the idea is that if the attacker can get access to the training data that is used in the machine learning algorithm to train the system, it could do things like make itself invisible to the computer vision system by saying, well, these are examples, say, photographs of me, but I tell the computer, there's nobody in this image. You see nothing. And hopefully that it would be trained properly. Or maybe you could make yourself look normal to an anomaly detection system so that it would not notice that you were withdrawing large amounts of money from other people's banking accounts. Or maybe you just want to slightly bias the behavior of the system so it tends to bid slightly higher on certain stocks in the stock market, or maybe put your advertisements on a little bit more often than someone else's advertisements. So those are the kinds of vulnerabilities that again, we need to deal with. The third challenge is an area that's known as mixed autonomy. So as I was, a good example of that is autopilots in aircraft. And very often the autopilot is doing fine, but then it gets into some very difficult situation where it cannot control the airplane anymore. And what it needs to do is hand over control to the human pilots. Unfortunately, if the human pilots have not been paying attention, then they have what is called poor situational awareness, and they make very bad decisions. So an example of that was Air France 447, which was that flight from Brazil to Europe, and the airplane ran into trouble in a very large storm, just at a moment when the crews were changing over who was the pilot. And so the pilots made a series of very bad decisions, and the very last words of the pilots, pilot one is saying, how is it that we are going down like this? Presumably in French, not in English. And the other pilot says, see what you can do with the commands up there, the primaries and so on. Climb, climb, climb. And of course, it was several months before they found any parts of the plane at all. So this is how can we make an imperfect autonomous system function well? We really need to think about these systems as combinations of people and machines working together, and we need to ensure that that combination is reliable. There was a story just today in the New York Times about the latest upgrade of the Tesla software, which lets some of the Tesla cars do a kind of autopilot on the highway. And I think we will see exactly this problem occur. And in fact, it's much worse in cars. In aircraft, you often have many minutes to make a decision to recover from a mistake. In a car, maybe only 200 milliseconds to make that same decision. A second problem, or a fourth problem, I guess, yes. The fourth problem I want to mention is really about the user interface between the human and the computer. So in the famous Disney movie, Mickey Mouse uses magic to tell this broom to fetch me some water. But he doesn't specify any, we would say in programming, any termination conditions. So so of course he didn't intentionally create an army of these brooms, but they eventually they bring so much water that he almost drowns in the water. So the problem here is, how can the computer understand what the user really intended rather than treating every input as a command? Of course, we have many ideas about how to do that. There's a lot of existing technology there, but it's a big challenge in every new system. So there is a lot of research happening in these areas. My group is involved in some of them. We have some techniques also at Big ML where we can do verification and self-monitoring so that the computer could be observing its own behavior and saying, well, usually I never do this kind of action in this situation, so maybe something is wrong. Maybe I've been compromised by an attacker of some kind. Or also, the computer needs to have knowledge of what is desirable and acceptable behavior. So bringing in so much water that Mickey Mouse drowns, that should be that's not good behavior. And improving the user interaction. Okay, well, let's now turn our attention to the third topic, which is technological unemployment. And this is a difficult topic for me because I am not a labor economist. So my knowledge here is based primarily on my reading of the work by labor economists. And here's one sign. There is some evidence that technology is already leading to certain kinds of unemployment. So here's some of that evidence. This is from Andrew McAfee, who's a co-author of this book, The Second Machine Age, that deals with these questions in quite a lot of detail. So this is U.S. manufacturing employment, and here is U.S. industrial production. And so we can see that U.S. industrial production, and this is using 1972 as the 100 point here, that production has more than doubled over this 30-year period, but our employment has dropped by 1/3. So this suggests that something is happening. And you might think, well, maybe this is partly the result of outsourcing, but that doesn't explain this, because this is just U.S. production and U.S. employment. There's some other interesting work by these guys, Frey and Osborne, that have looked at trying to evaluate for all kinds of different existing jobs the probability that they will be automated by advances in artificial intelligence. And so they've taken a whole different set of job categories here and arranged them in terms of the probability of being computerized, and the vertical axis is the number of people that work in those different kinds of jobs. And so you can see the jobs that are most likely to be computerized are things like service and sales, office and administrative support. And the things that are the least likely are things like education and healthcare, these areas here. So they predict, if you just look at this, it looks like we're going to have very high levels of job losses due to automation. Of course, this is not the first time this has happened. There was the complete or nearly complete automation of farming in the beginning of the 20th century. There was the Industrial Revolution over the 18th, 19th, and 20th centuries. And in the past, there have always been new jobs, better paying jobs that replaced the old jobs. The question is, what will those be? You can tell everyone, well, you should all become computer scientists, but that's really not possible. I think one of the things that has been so successful, for example, about technical trade schools, is that we can take a person of average intelligence and make them a very valuable member of society with very marketable skills. So what will the marketable skills of the future be? Well, I think there are a few reasons to be optimistic. One of these is that, as we've been discussing so far, artificial intelligence is often complementary to human skills rather than purely replacing them. Another reason to be optimistic is the usual one here, that as we get increases in productivity from automation, this leads to increases in wealth, which leads to increases in consumption, which leads to the demand for new kinds of goods and experiences, and that in turn leads to new kinds of jobs. So when we focus only on current jobs, of course we would expect those to be at risk. But this underestimates the creativity of people to come up with these new kinds of products and services and entire new industries. So what will be the new jobs? Well, I think one set of jobs will be these jobs involving hard to automate skills. So I think any job that involves high levels of social skill is probably something that computers will not be able to do anytime soon. The same with anything that requires a deep understanding of human experience and emotion. Because while we can teach computers to say, look at a picture and try to guess whether someone is happy or sad, the computer doesn't actually have experiences of being happy or sad. We don't have a way of creating training data to make a computer feel that way. And so I think anything that requires empathy is something that will be out of reach of computers, except as computers kind of would simulate it, but they won't have it. And again, anything that requires high degrees of creativity. I mean, Professor Lopez de Mantaras has worked on computers that can do certain kinds of musical composition, but I think that developing entire new industries is probably something that is very safe for a long time. The other thing that I want to mention is, as I discussed before, jobs where the human plus the computer is more effective than either one alone. And these are generally sometimes called augmented cognition cases. And so I already mentioned the idea of there's this game, or maybe I didn't mention it, but there's this game called Centaur Chess, and this is their logo here. And this is this idea that these are competitions where a person plus a computer plays against another person plus a computer. And the person plus the computer can defeat any human and also defeat any computer. But working together, again, the person makes the kind of strategic decisions, and then the computer works out all of the tactical details. Another kind of example, I think, is combining physical dexterity, which humans are still much better able to grasp things and manipulate things than robots, with information access. So there's some work that was done by this company, Metaio, using Google Glass, but we're seeing many other augmented reality headsets and virtual reality headsets becoming available. And so one can imagine, for instance, they have a demo on where they show a sort of overlay. So here you are, it's very hard to see in this picture, but I'm looking at my automobile engine, the engine compartment, and I'm trying to add fluid to the windscreen water, the cleaning reservoir. And I can't find it, but with the virtual reality, it's able, with a camera, to look at the car engine, recognize where it is, and then highlight it for me in green so I can see what I'm supposed to do. So you can imagine, I think, many kinds of repair tasks, assembly tasks, construction tasks, where maybe the construction worker of the future is wearing augmented reality goggles, and those are telling him, oh, look at this thing over here, there seems to be a problem here, or this is where the thing you're holding in your hand, it goes in this place here. Maybe that worker of the future is also wearing an exoskeleton so that he can lift 200 kilos of material and so on. So that's one other possible concept of the future. I think it's interesting that when things like routine physical activities become automated, what are the things that cannot be automated, that cannot be replicated by computers? And one of those are historical and cultural artifacts. So these may become even more valuable than they are now, and because computers cannot produce a new Roman Empire or a new Greek civilization, and certainly not a new Al-Andalus. So one can make the argument that artificial intelligence plus augmented reality might make visiting the Alhambra even more exciting than it is now, because you might be able to walk through those rooms and see the historical people in those rooms interacting with each other in a sort of in-place movie. So the final vision I want to discuss, how am I doing for time? Are you tracking me? Okay, perfect. The final thing I want to discuss is the vision of a lifelong personal AI assistant. So I was part of a project that was actually the predecessor of Siri on the iPhone, which was trying to build a personal assistant system. And the concept here is that when people and computers are working together, nowadays the way it works is that someone hands me a computer system and I have to learn how to use it, and maybe I become more capable with time, but it takes a long time to learn to use that system. And it would be nice if the system also learned about me so that we could become a very effective team. And so the vision here is that perhaps when a student enrolls in technical college, they are given a personal AI assistant. Maybe it's a robot, or maybe it's some sort of wearable computer, or who knows. And the student and the assistant train together. So they are taught the procedures of the company they work for, or the procedures of the trade they're learning. And they learn to solve problems together, jointly and efficiently. And then when you go onto the job market, the employer doesn't just hire the person. The employer hires the combination of the person and their assistant as a team together. So I would like to say the future is maybe more like R2-D2, the sort of personal assistant, than it is like the Terminator. Okay, well, let's now look way far into the future. What happens as AI technology continues to improve over the next 50 years or 100 years? Well, some people are very afraid, and I'm sure you've seen in the news Stephen Hawking warning that artificial intelligence could end mankind, or Elon Musk saying artificial intelligence is our biggest existential threat. And even our colleague Stuart Russell, who's the author of the leading AI textbook, says artificial intelligence is as dangerous as nuclear weapons. Well, I don't agree with them, and let me explain why. I think there are a couple of misconceptions here, and they're, of course, very common in the press, but also in the whole sort of singularity community, which I think Ramon will talk about some more. One misconception is that somehow artificial intelligence is there will be a threshold, a level, and once we cross that, artificial intelligence, robots will somehow wake up one morning and they will be conscious and sentient and super intelligent, or truly intelligent, whatever that would mean. And so there will be a moment when they become smarter than us. Well, if that's the moment we're waiting for, it already happened, because computers are already smarter than us in many dimensions. That's why we use them. Google is much smarter than any reference librarian in terms of knowing the contents of the world's reference material, books, statistics, all these things. So my colleague Tommy Poggio at MIT likes to say, intelligence is one word, but it means many different things. And so there's not just a single level where we say, well, at this point, the computers are smarter than us. It's more, there are all of these different dimensions of intelligence. People will always have some competitive advantages in some of those dimensions. Computers will always have competitive advantages in others of those dimensions. The other thing is that autonomy, right? I've been drawing this distinction between smart software and autonomous systems. Autonomy does not happen spontaneously. If the Google search engine sees another 1 million web pages, it won't suddenly become autonomous and decide it wants to start trading on Wall Street, right? It's a search engine. It won't do anything else. Systems need to be designed deliberately to be autonomous. And to be autonomous, this means they need to be given resources, money, electrical power, materials, manufacturing capabilities, and so on, in order that they can act in the world. And so we need to think very carefully about when we give computers that kind of autonomy, just as we would giving any person that kind of autonomy. We don't give you $1 billion and say, have fun. So I think the danger of autonomous AI is not really about the artificial intelligence part so much as it is about the autonomy part. Because if we have an autonomous system, even if it has no AI in it, it could consume vast resources. It could injure and kill people. And of course, it could apply artificial intelligence to help it do those things. But it's really the fact that it would be autonomous that's the problem. Well, so why do we want to make systems autonomous, and how can we maintain control of them? I think that's really the central research challenge that the AI field is facing. And I think there are two cases we can consider here. The first case is when the decision making is occurring at the same rate as human decision making. So if we think about the aircraft autopilot or most robots working in factories or surgical robots, we can supervise them because their decision loop is the same speed as ours. And so it's very much just like supervising a human being in a human organization. The other case, though, is very high-speed decision-making. So examples are things like the stock market and the famous flash crash from October, or was it May, of 2010? I don't remember now. Or things like the electric power grid or the self-driving cars, where the decision-making is happening faster than people can really do this. So there was a paper that came out recently that suggests that not only was there this big flash crash, but there have actually been thousands of small crashes happening at less than 1 second time intervals, less than 950 milliseconds. And so, this, of course, one solution here might be just to slow down the markets, but we can't really slow down the power grid or the cars. So one possible solution here is automated monitoring, and there's a lot of research going on right now in trying to find signals that can detect these flash crashes and other kinds of anomalies. And so I took this from a paper that was published recently where they're simulating flash crashes and showing that each dot here is a trading system, and the green color is about their inventory of shares, and when the crash is happening, the network becomes hyper-connected and the inventories change hugely. Everybody has extra stock they're trying to unload. So we can do that monitoring, I think, but what do we do when the monitoring detects a problem? With stock markets, we can halt trading and actually unwind the transactions. But with the self-driving car, what should it do? Or with the smart electric grid, what should it do? So each of these systems, we have to have a strategy for dealing with this safety problem. So the final thought I want to leave you with is I think we should never create a fully independent autonomous system that is not under direct human control. And by fully independent, I mean a system that we have lost control of. That would be an error. And so to finish then, just to summarize my presentation, artificial intelligence has been making steady progress. It seems like it's been accelerating, but I think, in fact, it's been very steady all along the 60 years of the field. We can see some exciting applications of tool artificial intelligence are coming soon. There are potential applications of autonomous AI being proposed, and I think we need to be very careful about ensuring the safety of these systems before we bring them to market. In terms of technological unemployment, information technology does seem to be or may be contributing to unemployment. The picture is not clear, and perhaps there are futures where there will be many new and interesting kinds of jobs. And then I want to reassure you that tool AI systems will not spontaneously become autonomous, develop free will, and want to take over the world. But it is important that we find ways to, when we give computers some kind of autonomy, that we have ways of controlling that. And with that, I will stop. And I guess we'll have questions later, yes? Is that right? Yes. Thank you very much.